Hello and welcome back. Today we are going to review Unit 4, Exponential and Logarithmic Functions. I'm going to break this review into two separate videos because exponential and logarithmic functions are a big important part of Algebra 2. And a lot of this, especially logarithms, you have not seen before this course. So I want to spend a good deal amount of time going over what they are and how to solve them and how to graph them and what they are and such. I'm going to break this into two separate videos. As you can see, in the video 1, we will be doing the lesson overview, all three slides of Common Core standards. There's a lot of Common Core standards associated with this unit. And then we're going to get into some topical reviews. In the next video, I will do the remainder of the topical reviews and have the lesson summary of the most important things in this unit. Okay, in this unit we had 14 lessons. The first half of the unit, up to lesson 7 in the unit, was essentially focused on exponentials. What are they? How to find equations, how to solve some with common bases, and so forth. And the second half focused on logarithms. What are they? How to graph them? What are the laws of logs? How do you solve exponentials using logs, and so forth. Okay. So those are the two main things in this particular unit. Now, even though I'm doing two videos, just keep in mind that I'll be looking at both of these topics throughout each video. There were several Common Core standards associated with the Common Core standards. Okay. So with this unit, the first set on this slide, are talking about number sense. That's what the N stands for in algebra. Number sense, RN stands for real numbers, and CED, creating equations. So pause the video, just get a sense for these standards before moving on. There are also several function standards. F stands for functions. IF stands for interpreting functions. So just pause the video now, just get a sense for what these standards are saying. And lastly, the remaining function standards. LE stands for linear, quadratic, exponential functions, and BF stands for building functions. So pause the video now and get a sense for these standards as well. Okay, so as you can see, there's a lot that we did with exponentials and logarithms that we're going to be expected to be able to do with them. But first, let's just look at the very basics of exponential and logarithmic functions. What are they, and how do they look like? What do they look like? So, let me provide some examples of exponential functions. An exponential function is any function that has the variable as an exponent. So y equals 7 times 5 to the x. That's exponential because the x is an exponent. You might also see functions using function notation. So f of x is equal to maybe, for instance, 1/2 1.75 to the x plus 5 minus 7. It's a little more complicated looking, but again, it is an exponential because the variable is in the exponent. A log function is just the inverse of an exponential. Before I show you an example, let's just talk about inverses briefly for a moment. So if I had the function y is equal to 2 to the x, and if I ask you to find the inverse of that function, that means you switch the x and the y, so you get x is equal to 2 to the y. But we didn't really have, up until this point, a way to get rid of that y as an exponent. So what we do is we define something called a logarithm. So if I take the log base 2 of both sides, it allows me to cancel out that base of a 2, leaving me just y is equal to log base 2 of x. So y equals log base 2 of x looks a little better, is an example of a logarithmic function because you're taking a log of a variable. Now just a word about logs before we go on, and exponentials. There are a bunch of common types of bases in logs that you've seen before. Okay, and the first one is the number e. Y equals e to the x. Okay, that base of an e as an exponential has an equivalent logarithmic form. Okay, natural log of x. Natural log of x is really the same thing as the logarithm of base e. Those are inverses of each other. Another very common log that you saw this year dealt with a base of 10. And that is seen when you have log without a base written. So if there's no number written in that base, it is assumed that it is log base 10. In your calculator, by the way, whenever you're doing logs, notice it has log button and an ln button next to the 7 and the 4. Those are the only types of logs that your calculator can do. Your calculator cannot just immediately evaluate log base 2 of a number. Okay, it can only evaluate log base 10 of a number, log base 10 of 7, or the natural log of 7. That's the only thing your calculator can directly do. Of course, there are ways to manipulate logs in order to get it in a form that we can type it in our calculator to simplify, but more on that a little bit later. Pause the video now, write down anything you need to before moving on. Now another crucial thing you should be able to do is be able to convert between exponential and log form. Now they are intricately related because they're inverses of each other, so you should be able to easily convert between each form. I'm going to provide several examples dealing with some common logs, some natural logs, and just some other bases for logs. If I have the exponential equation 5 to the x plus 3 is equal to 27, and I'm asked to convert that into log form. Okay. Before we actually do that, I just want to point out some terminology that are used in these logs and exponentials. So on the top I'm going to write a to the b is equal to c in the equivalent logarithmic form, which is b log base a of c. This is how you're going to convert between the two forms. Okay. Notice between both of these forms that a term, or variable or unknown, whatever it ends up being, is called the base. And the b in what I have written is called the exponent. Notice the base in the exponential is what you're raising to a power, and the base in the log is what you're taking the log of. The exponent of the exponential is equal to what the log is equal to, which brings me to something I just forgot to mention on that last slide, is that logs are essentially exponents. Okay? Notice the exponent is equal to something from the exponential form. So if you're converting to logarithmic form, what you're going to do is you're going to say the exponent of the exponential, which is x plus 3, is equal to log. In this case, we had 5 raised to the x plus 3, so it's going to be base 5 of the 27. Let me give you another example, maybe involving natural logs. So if I had e to the 5x is equal to 1/2, again, converting to logarithmic form, the exponent is the 5x, is equal to, because we're base e, it's going to be the natural log of 1/2. Because remember, natural log is the same thing as log base e of 1/2. Now going the other way, going from logarithmic to exponential form, we do the exact same thing, we just think backwards. So if I have the equation 5.7 is equal to log base 8 of x plus 3, and I'm asked to convert that into exponential form, the base is 8, the exponent is what the log is equal to, so raised to the 5.7 is equal to the x plus 3. So this base gets raised to that exponent. Now another example, let's say I have x minus 3 is equal to natural log of 5. And natural log is going to immediately tell you you're going to be dealing with log base e of 5, so e is going to be your base. So e to the x minus 3 is equal to 5. And one more example, negative 1.23 is equal to log of x. Okay, notice if I don't have a number written here, that's automatically log base 10. So this converts into 10 to the negative 1.23 is equal to x. Okay. Pause the video after each slide to write down anything you need to. Now the laws of exponents and logarithms are very similar between the two. Okay? Because they're inverses, they're going to be very similar to each other. So I have logarithms and exponents. So what I'm going to do is I'm going to show you the product laws and the quotient laws and the power laws for both of them. And at the end I'm going to show an example of how these laws are commonly applied. The product law for the exponentials expressions are when you're multiplying the same base together. So if you have base a to the x times base a to the y, the product law says if they're the same base that you add the exponents. So it becomes a to the x plus y. Just to give a quick example, if I had x squared times x to the 5th, that would be x to the 7th. 2 plus 5 is 7. Now, because logs are essentially just exponents, I can apply that law to the log of two things we multiply together. Say I have log base a. Because log is an exponent, you're essentially multiplying them together, so you have to turn it into addition. You add the exponent. So log base a of x plus log base a of y. Notice the comparison between the two. Hopefully you see how they are related to each other. So for instance, if I had log base a of 20, okay, notice that's not written as a product, but I could write 20 as a product of 4 and 5. So 4 times 5, which means it can be converted into log base a of 4 plus log base a of 5. The quotient laws are when you're dividing by, in the exponential form, dividing by the same base. So a to the x over a to the y. Same base. So what you do is you subtract the exponents. That's the quotient law for exponential expressions. So for instance, if I had x to the 10th over x to the 7th, that gives me x to the 3rd. 10 minus 7 is 3. In logs, if I have log base a of x over y, now remember they're still exponents, so it's going to be log base a of x minus log base a of y. Okay. So for instance, if I had log base a of 9/5, then I can say it's log base a of 9 minus log base a of 5. The last law is the power law. So that is when you raise an exponential expression to another power. So a power to a power. And what happens there is we multiply the exponents. So it becomes x times y. So for instance, if I had x squared raised to the 5th, that would be x to the 10th. For the logarithms, if I had log base a of x to the y, notice it's an exponent raised to an exponent. Then I multiply them. I multiply the exponent with the exponent. So that essentially this y gets placed out in front. That's the power law for logarithms. So if I had log base a of 2/3, that's the same thing as 3 times log base a of 2. This power law for logarithms ends up being one of the most important log laws, especially when you're solving equations, because when you solve an exponential equation, your variable is an exponent, and notice it allows you to bring that exponent out front if you use logarithms. Okay. More on that a little bit later. Now, one common application of these logs properties occurs when you're asked to do something like this. If you were given, for instance, that log of some base, say a, is equal of 2 is equal to 0.46, and let's say you're given the log of the same base of 5 is equal to 1.07, you might be asked to find something like the log base a of 20. Okay. Don't know what the base is. There are ways to solve for it, but we don't technically know what the base is at this point. Okay. What we can do is we can use the property of laws in combination with log base a of 2 and log base a of 5 to rewrite log base a of 20. Now I'm going to find ways of representing 20 in terms of bases of 2 and 5. And what I notice in this particular case is that 20 can be represented by 4 times 5. 4 is 2 squared times 5. Notice the application of the laws up above. I have the exponent law, the power law I'm going to be applying, and the product law. Okay? I'm going to have two laws I can apply to that logarithm to reduce it further to just log base a of 2 and log base a of 5. So this becomes log base a of 2 squared plus log base a of 5. That's applying the product law. Now I can apply the the power law on the first one to give me this 2 out front, so it's 2 log base a of 2 plus log base a of 5. And notice because I was given that log base a of 2 is 0.46, so I can substitute 0.46 in for log base 2. And I know the log base a of 5 is 1.07. So then I can use my calculator to finish this off. So this gives you 0.92 plus 1.07, 1.99. So log base a of 20 is equal to 1.99. Okay, so it's just an example of how these properties are typically applied. Not the only way, but this is a common way. Now let's look at negative and fractional exponents. This is another thing that we've looked at in this exponential unit. And if you have a base raised to a negative exponent, what that just means is that you reciprocate it, meaning if it's in the numerator, it goes into the denominator and becomes a positive exponent. Likewise, if you had a negative exponent in the denominator, it goes into the numerator, so it becomes a to the positive x. Fractional exponents, so if you had something like x to the 2/3, okay, the way you're going to analyze this is that the numerator and the denominator represents different things. The numerator represents the power of the base, and the denominator represents the root of the base. So we're going to be dealing with square roots, cube roots, fourth roots, and so forth, and raising them to powers. Okay. So this x to the 2/3 can be written as x squared taking the cube root of x squared. But you could go either way. You could do the square first and then the cube root, or the cube root and the square. So you could also rewrite this as cube root of x parentheses squared. The root is 3, that's the cubed root, and the power is 2, that's the square. Okay, so just another example, 17 to the 3/5 can be rewritten in two different ways. One is the 5th root of 17 cubed, or the fifth root of 17 all cubed. And if you combine the two, note if I had something like x to the negative 1/3, note that that becomes, with the negative exponent law, is that you raise it to the positive exponent by putting the denominator, reciprocating it. And then I'm going to apply the rational exponent law, which makes that into the cubed root of x to the first, which is just x. Okay, and the last thing I want to do in this video is look at the graphs of the exponential and log functions. Just before we get to the graphs, just a little word about the bases, so, and what they look like. So an exponential is something of the form b to the x, and a log function is something where you have log base b of x. Okay. Remember, they're inverses of each other, so graphically they will be a reflection of the y equals x line. Okay, so if you know how to graph the exponential, you should be able to easily graph the logarithmic functions with that in mind. But before I do the graphs, I just want to point out something. This base can never be negative, and it can never be 1. Reason being, okay, if you consider a base of negative 2, for instance, and raise that to an exponent, what we just saw with the fractional exponents is we could have any kind of input for x, so we could actually have 1/2 as an input. And we know that 1/2 as an exponent is the square root. And notice that that is not a real number. Okay, that's in a future unit, but we've already learned that that's not a real number. It's an imaginary number. However, I take root 2 to the 2nd power. That gives me positive 4. It works. So negative numbers, there's some really weird things going on with negative numbers. So we never consider them as a base of an exponential, because the graphs would just be wacky all over the place. Okay. Another reason why we don't include 1 as a base is because if we raise 1 to any power we want, it's always going to be 1. Okay, raised to the 10th, raised to the 6th, 1 raised to the 1/2, 1 raised to the negative 1. Any input we have will always be 1. So we're not going to consider the base of 1. And because logs are inverses of exponentials, we're still going to have the same rules. So let's look at the graphs of these. So we have two different types of each of these. We have growth, and we have decay. Growth occurs when the base value is greater than 1. Decay occurs where the base value is between 0 and 1. Again, notice we're not considering any negatives or the value 1. Growth looks like this. It always goes to the point 0, 1. Because if I put the input of 0, that's going to be raising whatever the base is to 0 power, which is equivalent to 1. So the point you're going through is always 0, 1 on both of these, regardless of whatever the base is. Decay looks like this. It also goes through 0, 1. Now note the domain and range of the exponentials. Okay? The domain is all real numbers. The range, y is greater than 0. And the reason why it's greater than 0, not equal to 0, because it approaches something called an asymptote. Asymptote. And that asymptote is going to be the x-axis, sometimes referred to this equation, y equals 0. Okay. So you can put anything you want into an exponential, you'll get an output that is positive. Now, of course, in future units, we looked at shifting these graphs up, down, left, right, and so forth. So the asymptote is not always going to be the x-axis. The intercept on the y-axis is not always going to be the point 0, 1, but these are the parent functions. And these are where exponentials start from. Okay. Logarithmic functions are the inverses. So we have log with growth. Now, inverses, recall that the coordinate switch. So if 0, 1 is on the exponential, 1, 0 is on the logarithmic function, on its inverse. And for decay, also goes through 1, 0. But take a note of this. For the domain and range, the domain are only positive inputs because we have another asymptote. If the asymptote was the x-axis for exponentials, it must be the y-axis. That's going to be the asymptote. For log functions, because you flip the x's and the y's, switch the x's and the y's, that's where the asymptote is going to be for log functions. So the domain is x is greater than 0, in the range is all real numbers. So this also points out a very important topic and fact about logs. You can never take the log of a negative number. Or put it in different terms, you can never evaluate a log of a negative number. Okay. So you'll never be able to do something of log of negative 2. That will never, ever occur. Okay. You'll never be able to do that. And you'll never, by the way, be able to take a log of 0. Okay, because notice the parent function for log function will never hit that y-axis, so you can never have an input of 0. So if you're ever asked to find the domain of a logarithmic function, then what you're going to do, say we have log y is equal to log of x plus 3. We're going to set whatever we're taking the log of, so in this case x plus 3, that must be greater than 0. The domain says whatever the input is into the log, whatever we're valuing the log of, it has to be greater than 0. So in this case, if we were evaluating the log of x plus 3 must be greater than 0. Which means I have to be greater than negative 3. So if I plug in negative 3, I get 0. Plug in negative 2, I get 1, so that's possible. You can take the log of 1. So that's just a little side note about logs. Okay, thank you for watching this first video of 2. In the next video, we're going to focus on writing the equations of an exponential function, Newton's law of cooling, solving these equations, some compound interest formulas, the percent manipulations and how to interpret them, and also the summary for the most important information in this unit. Thank you for watching, and I hope to see you in the next video.